Well, thank you. I am very happy there is so many people interested in MLOps and pipelines. Believe it or not, 2 or 3 years ago, this room would have been empty. But that's amazing. So yeah, I'm Lex. I'm the head of strategy at Avstreikh. We are a Swedish company. Just this is probably the one slide about us, so bear with me here. So we are what we call an AI lakehouse. We support essentially data lake and real-time data for real-time, batch, and ML systems. We've been operating for 8 years now, and we're pretty engineering heavy. So yeah, we deployed at scale-ups and large enterprises. Oh, sorry. Oh, okay. Yeah, now I can hear myself too. Right, yeah. And so, yeah, we operate everywhere, and we are publishing an O'Reilly book in a couple of weeks. The author is over there, hiding. So if you want to know more about that, you can ask him later. So more about MLOps and pipelines. First of all, is what do we know about it? Is that we actually operate quite a few of them for fairly large entities and enterprises. Some of which you may know, some of which you might not have heard about, but yeah, typically large organizations. So it's a scale issue, right? It's not necessarily an issue of building models. It's really an issue of managing a large amount of data in an operational setup for production so that it works in a product. So that's what we specialize about. So I think it might be interesting to just go really quickly about the problems we are trying to solve. And the first one is something that I really like to point out is that we have no idea how models will behave in production until production. And this is a meta study that was sort of published last year. And objectively, it's still quite true. In the in production environment, you had a lot of ideas in development environment, you had a lot of ideas that once you try to put it in production, it stopped working. So you don't really know why. And that paper really sort of captured that. The second issue, or let's say the core issue is okay, you can go. The second issue is the management of the support of the AI workloads. And so this is not a small company, this is not a small study, but end of last year, they essentially showed that, even in enterprise setup, a lot of organizations cannot just support the workloads, or their architecture can't support AI workloads. We're talking real-time workloads and so on. And so that's what we're gonna talk about. The core challenges now, like the actual aspects that we are trying to consider is one of infrastructure. So it's maybe not such a hot take, but it's a little bit of a hot take. I'm not gonna talk about how to do better models, and I'm not qualified to do it, so it's not gonna matter. It's really more about having production AI systems that are able to support production, and it's a data and infrastructure challenge rather than a model challenge. So less so about training, but more so about managing the data and the state of that data. The second point is really when you think of machine learning systems, it's not stale data. It's not coming from a CSV file necessarily. It comes from different sources. That's also what you're trying to solve, is to manage this diversity in the data sources that you need to combine to actually create a model that then you need to put into production. And so that's one of the core aspects that the system and the mind map that you will have to have needs to solve. And the other point is that all of that has a different temporality. It's a different time series. So maybe some data comes from last week and is updated every week, and maybe some data is daily updated, maybe some data is updated hourly, and maybe when you have an operational system, you need to actually consider and actually fix all that. And finally, transformations. I'll spend a bit more time on that a bit later, but the transformations in this sort of systems is slightly different than the pre-processing you will have like on the data warehouse side, which is like the normalization, the scaling, the encoding that you might need to do. All of this adds a layer of complexity in the operational system that many organizations will not necessarily see until they actually try to operate them. So how does it look, elsewhere? Or, are we talking about just pipeline or maybe architectural diagrams and so on? So if I look at what Google does or what Google suggested, it's this sort of operational flow. And that's not inherently bad or wrong. It's in fact fairly probably correct. But those are like boxes that they want to tell you to fit and to fix and to manage and all the things that might save your life or maybe not. And so the problem here is that this is one part of the system, but this is eventually just a batch system. It's not a real-time system. You'll have to have all that all over again if you need to support, let's say, real-time systems. And similarly, if you go to the Databricks side of thing, they will tell you, well, those are all the boxes and all the things you need and to solve all of your, all your issues of operation and make your life resilient and so on. Now, the question is, is this really production? And the consultants, I'm sure there's a few, but there is, many types of consultants. But some consultants say, yeah, that's amazing. That's what you need for production. Pay me 1 hour per box, and I'll manage all that for you. And our argument here is a bit different, evidently, but I would say maybe this is not exactly the problem we are trying to solve. So, just I'm sure in the few items I will show afterward, a lot of you already know the core aspects, but some of you might know only partial aspects of it. So I'll just reiterate some of those things. So what do we, as an organization, consider MLOps? So first, it's all about the data, the features, and managing, how it's ingested, transformed, and so on. Then the models, because you obviously need to train and have a model, and you need to validate them, deploy them, and serve them. And then finally is the inference. Now, once you have this sort of very basic pyramid of the flow of interaction between the data and the models, you need the operational layer on top of that. For us, that will be everything is versioned. Everything can be logged back so that you can actually see the results and compare and monitor. And finally, you want to automate all that. So on a very, 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 very basic level, on an abstracted level, for us, that's one view of machine learning operations. Automation, versioning, logging of the data, model, and inference, essentially. And you need to productionize that. Now, the second thing that I'd like to sort of introduce to express the sort of complexity of operational layer is the model lifecycle. So let's imagine you have different type of data coming at different cadences with different temporalities and maybe different types and so on. If you want to do a model, typically you just take a snapshot of that data, you create your training data, then you train it, and you have a model. Now, in an operational system, the data is not stale. It doesn't come from Kaggle. It comes from an operational layer, something that moves, that continues to live. So you might have some level of accuracy, but that accuracy will usually decay over time. It's super, super easy to know, to sort of express that in your head. If you don't know about it, is like ChatGPT has been trained until last October. As time goes by, there is a decay. There is a sort of degradation of the knowledge of the model for what it's supposed to predict. And that's true for, evidently, any models in production. So what happens is when it reaches a certain point, you'll essentially just retrain. Maybe you have better information, maybe you know more about how the model operates and so on, and so it gets better and so on and so on and so on. And so this is sort of the other aspect of operation, is it's not gonna be stale, it's always in movement, so you need to account for how to manage that, how to be sure that you can always retrain without breaking things, how do you always have the same sort of data types, schemas and so on that are managed so that you can have the things rolling in production. So what happens in between, why it happens is, well, I'm sure you all know, it's the seasonalities. Maybe on the weekend, people order things differently, so on and so forth. It might be just that the data changes over time. So how do we consider, how do you supposed to be building pipelines? So it's not going to be really architecture. I'm not going to tell you, oh, you need this sort of software and so on. But how do we see the pipelines? So first, evidently, those data sources, and well, evidently, at one point or another, you want a prediction, and things happen in between. So what happens in between, I think, depends on the type of data that you want to actually use. So I'll just show a small table on the left. There is an order, there is a time column, a location, and items, and that will be sort of useful for later. So then I want to predict the order, so I want to predict the future orders, and some magics happen in the middle. So typically, data pre-processing, training, saving the model, so on and so forth. Now, if I want to do that for one permutation of that initial data, that's nice, but that's not how it works in the real world. In the real world, I might want to do that for another permutation. So maybe I have a different combination of item location that I want to predict the demand for without changing the initial data, and maybe another one, and another one, and another one, and another one. This use case is real, by the way. That's a big automotive, and they want to predict the demand per location of certain items, and they essentially have 2,000 models that they need to manage. The small models, not like an LLM or anything, but they have 2,000 models that they want to manage. And so if they do it in this sort of way, they will end up with having like a lot of those processes here, and essentially like a very large monolithic program in between each time for each of those models. So that's not what we ideally want. Now, in another hand, all of that is, even in enterprise, largely done in Python. So we can do all that data cleaning, pre-processing, and extraction, and so on in Python. But it still has a big problem by just looking at it at this level anyhow, is that, well, you can't really reuse the same data easily. You can't manage the resources efficiently. If your model is dependent on certain speed or latency requirements, again, very hard to manage. And then there is maybe some consideration of governance, because maybe it's in one system, probably in the cloud, maybe it locks you in an ecosystem, not essentially very easy to do. So what we want is that thing I showed earlier, somewhere in between. And so the way we do it is like we divide it in 3 categories of pipeline. So, this is wrong, here. So feature pipeline, training pipeline, and inference pipeline. In our view of the world, you can essentially break down any machine learning operational, let's say, system into those three pipelines. And the job is to modularize and parameterize those pipelines the most efficiently possible. So, yeah, I just said that. Evidently, you need an output. Let's imagine you have an LLM. You can have a human in the loop on the inference side. All of that can be done. And eventually, you can have like logging and monitoring, etc. So I'll be more interested in the middle part. And I'll try to explain how, what would be the ideal sort of way to operate those parts in order to be able to operationalize. So one thing that you don't want to do is to actually pass the output of each of those pipelines to the next one, because then you've solved nothing. You do exactly the same thing as before, but in a different fashion. So ideally, you need a data layer. You need a state management that actually allows you to save the state of those pipelines or their derivative, the models, artifacts and whatnot, or other assets in a data layer or state management. That allows you, in response, to have like a bit more of the governance aspect and the modularity, which I'll just show you just after. So we have few abstractions. I'm not going to go into it in depth, but there is few additional abstractions that you can have, such like having data that is not directly mounted, directly written into those pipelines, maybe just mounted, external tables. You might need some online data, etc. But on the high level, that's more or less how it should look like. Now, let's say the benefit of doing it this way is that you sort of like separate the programs from the state. So you can manage the program individually, have them being managed by the appropriate team. Maybe the feature engineering team is not the same one that does the modeling. So they all take care of that. And then you have the state managed as an infrastructural layer. So if I go back to that example I had a bit earlier with the table, the orders, etc., and how, for example, in that context, they would be using this framework to do 1,000 models, it's pretty simple. So they will just insert a data frame. This is pseudocode by and large in many ways, but like they will insert a data frame. I mean, this part is actually exactly how we do it, but the rest might be a bit pseudocode. And then you can apply some runtime parameters depending on your requirement from training or inference. In that case, I will apply the same filters for item in location to just train on that data frame that I would retrieve from the state layer, which will not change nor the original source nor the pipelines on the feature engineering side. And I can use exactly that to save a model, then use it for inference when the requests are passed, and therefore to filter on the query and filter on the logging. So I will know, let's say, the ground truth of all of those models will be known to me on a filtered base without changing any of the original data, and that creates a very operational system. So again, I didn't change anything on the data sources, which means that eventually if I have to do that 1,000 times, might be to do 1,000 models or to do tuning or anything, that will just work. Nothing has changed, it's just parameters. So it's highly scalable. Now, if I look a little bit in detail, like just in the feature engineering pipelines, oftentimes that's the part that's more interesting to me, or the part I can talk about a bit more. It will look a bit like that. So I took a CSV in this case because it's an old presentation, but imagine it's an actual stream or some sort of live data. In that case, you will do some pre-processing, and you will have a table that you will, you will define depending on the use case, maybe on the cadence, maybe on the source, and you will end up with many of those tables that are clean. Now, you need an interface for the model. In our context, we call that a view. It could be a feature view. It could be just a view, which will be the individual mapping of all the features that you need, their transformation, and the schema, the type, and the sources. So that will be more or less, oh yeah, just a little thing that I should mention before. That will be the engineering that is model independent. So it doesn't matter for which model do you produce this data. And that will be sort of to a degree, some of the engineering that you will need to do that are model dependent. So you could have 100 views with different types of transformation, different type of mapping for the model that are totally independent from the actual sources and the tables that you create. So that's how you do like feature engineering in our context. And so once you have that, you have the feature pipeline on one side, you can start building training data sets, you can start creating models, and the idea is that you can actually scale and create more models, et cetera, et cetera. And so you will have a training pipeline independent from the engineering pipeline. And the question is, if I go back to all the things I said before, is it actually an MLOps sort of a flow? I can sort of show you how. So if you have all those components, let's say, set in that manner, you can then start to do comparison. So if I compare the untransformed training data set to the original data set, and let's imagine it's an actual non-stale data, you can see distribution changes and such. And that allows you to monitor things like drift, like data drift. So at this point, you can say, well, I need to retrain a new model and maybe a new iteration without actually changing anything in the pipeline itself. So the additional benefit is obviously versioning, but that's sort of like doing new assets on top of that. As I said, the view, in our case, it's an abstraction that doesn't have data in it. It's just metadata, so you can do as many views as you want. And so, yeah, that allows you to do a lot of different iterative steps to do like different type of models. Finally, provenance, sort of, in our case, this is not how the lineage works, but you have a view of which model uses which data from which sources, has been trained on which training data set and so on. And it can get a bit more complex than that, evidently. That's actually how it looks like for us. And it can go until the model deployment and the actual serving interface, so you will know which model that is currently being deployed has used which view that uses which data that can be even derived from other data, et cetera, et cetera, et cetera. And all of that being version, you can actually, again, duplicate that ad nauseum and so on. Now, the main thing for us, the main abstraction, I would say, that makes all of that sort of scalable and possible is that view that I spent a bit of time there. And because it doesn't have data per se, we actually also record the type of transformation that each of the models will need in that view. So that will be something like that. It's like an actual Python, I guess it's a UDF, and that you will actually be applied on retrieval. So this is not applied on the original data ever. It's applied, I mean, unless you query it, it's applied on the query. And therefore, that's what makes it repeatable a lot of time. Because let's say that you would want to apply a min-max scaler on only a subset of the data, that would not be the same. The distribution would not be the same if you apply on a whole data set, say. And so because of that, you don't want to apply it directly on the original source, because then it just makes everything harder to operationalize. So ideally, if you set that up properly, you can retrain independently from the engineering, and that allows you to do many more features, create many more engineering logic independently from your modeling, essentially. And so that's how you operationalize that. Now, all of that can be and should be perhaps Pythonic. It's called PyData. In our case, it is, and that's sort of also one of the benefits of that object over here, is like we actually, this object here, although in this context there is only one table, this one feature group, but you can imagine it can have like 20 tables, and all of them might not be exactly with the same, not the same time series. So what that object does as well, it's transpiling the query into SQL to do a point-in-time correct join. So if you have misaligned rows, or like you don't want to give to the model data from the future, or they just like the cadences and the temporality of the data is not the same, this object will essentially know it, and it will fix it for you essentially. And so the point here is that it also has like that ability to create complex joins essentially. That's all right. Pick it up. And so in our context, we essentially try to divide it in 3 use cases, like batch, real-time, and LLM. That's sort of like where the market is at the moment. And the question is, would it work for either all of those use cases or not? And the answer should be yes. And the answer should be with whatever tools you want. Because one of the things we see in the industry side of things is that, well, it's moving extremely fast. Some frameworks are popping from everywhere. Like DubDB 3 years ago, it was sort of a more obscure thing. But now in enterprises, people are like, oh, well, I'd like to get a bit of that as well. So you want to be as independent as possible on the sort of program layer, on the frameworks that people can use, because that allows you to be much more nimble and operationalize faster. And so in our case, yeah, we support, the idea is to be as open as possible, no DSLs, and bring your own shovel and use whatever the best tool you may have for the job. So for batch, that might be SQL, Polars, Pandas, and so on. For real-time, that will be a bit more specialized because you might have to deal with real-time streaming. Again, should be fairly agnostic to that. So Flink, Feldera, which is I think it's a company in the US, but there is like a few frameworks that are popping up on that specific management of real-time data. And again, should be independent from the training and inference. So again, you can use like the best framework for the job. So that's the benefit of this view, which doesn't have like 100 systems around it, but like feature, training, and inference independent. And now for LLMs, you will just probably bypass the training aspect, although you can fine-tune still. But eventually, you still want to pass data from the data warehouse, like, I don't know, user data to the LLM, so the LLM knows about, the user that is maybe talking to it. So you will still need this sort of system to be deployed for an LLM. I think that's about it. I'm talking a bit fast, I realize that. Apologies. I can't be slower. Too much coffee. But yeah, you can try the platform. It's available for free in the cloud at the moment, so that's a serverless deployment. The only limitation in that version would be that we do not provide like a managed compute in the sense that you cannot have DAGs and all, but the storage, the APIs is exactly the same. So that's fairly nice. And yeah, if you want to read quite more in details, in more accuracy as well, I'm sure you can check the book. So For the book, we're gonna have a full digital copy in like 2 weeks' time, I believe, that we will be sending out to all the people who require it. And another shameless slide in, we are organizing a free online small conference, which is called the Feature Store Summit, very specialized on the storage. So for people who are more into the platform architecture and the logics behind it, there is quite a few nice speakers from, I don't know, Uber, Lyft, Zalando, and so on that will talk about this type of storage layer technologies. And yeah, that's it. I'm gonna stay on this one.
Questions?
Hi, nice talk. I come from the industry 4.0 world, so I'm working in manufacturing. And a few years ago, we were talking a lot about feature stores and how to embed that in our use cases. And I feel this has been going down a bit. And I was wondering if you know what are the use cases today for this kind of solution in feature stores. What I remember was the thing at the time was that in this SCADA system, the supervisory of the machines, etc., it was very, very important to capture this, what you mentioned, like when you have the feature and the aggregation that is done in a certain feature, how that evolves over time. So also a second question is in how it works for the tracking of modifications on the definitions of the aggregations that you do over time. Yeah. And how that maps to the database systems.
So for the evolution, I mean that's probably where I can speak the most, because I've been there since almost the beginning for the feature store, sort of like when it started to emerge around 2019. I arrived in HopsWorks in 2020, so just at the very, very early stage, before Feast was a thing, before all the open source stuff existed. We saw that happening. What happened at one point is that some technologies try to do one thing, let's say aggregation or query engines or DSLs to do better stuff. And that seems to be the thing that is slowly dissipating and dying. What happens is that it needs to be part of a bigger platform, because the feature data is so close to the model, it's so close to the data sources, that it can't be just a small tool in the middle. It needs to be an actual, infrastructural thing that takes care of a bit more. And so what you see emerging in the very, very, very large companies like AWS, Google, Azure is exactly that. All the small individual vertical sort of better engine specialized stuff, they disappeared, like 90% of them. And all the more like complete platform are the things that are sort of emerging and sort of becoming a standard. And it seems to be the case even in enterprise, where they have their own end-to-end platforms rather than small specialized thing. That's what we see. And then the benefit of doing that is like adding capabilities like real time and such becomes more complete with the training and so on. So yeah, that's where it's going. Like vertical technologies for feature storage are essentially dying. I can talk about that in private. I can share a few death stories. For tracking of the transformation in lineage and all, I mean, it sort of depends on how you set up your engineering pipeline. I think it does depend on what you want to track as well. So, like if you are engineering a new pipeline, it's a new version typically. So it won't organically change just because it changed. Now, if it's something that happens at the source, well, I didn't show, because it's not a product demo, so I didn't show the UI, but we actually version the schema, we version the data. So you will change the schema, you'll drop a column, that's not gonna work with the same pipeline. It's gonna happen a new pipeline right away. So there is like ways to prevent the underlying system not to break if things are changing at the origin. So, yeah. But for more details, maybe a demo would be better. Happy to do that.
Thank you very much for a great talk. I have a question regarding the dependency, especially between the training and the inference. Are you imposing any kind of constraints on the dependency your user can basically use, or and how are you managing this kind of stuff?
So the answer is as little as possible. Like we maybe not supporting the whole world of possibilities, but the deal, I mean, the thing we are trying to do, and I mentioned DSLs a few times, and the reason why we don't want to apply a DSL is because it will lock you into a certain view of the world. Our view is we want to abstract away complexity on the storage and how it's managed. The way you do the training or the inference, sort of up to you. We have preferences, but the bottleneck, I call it a purposeful bottleneck, is on the storage data, the way we store and retrieve the data. So then we try to be.
So you're really focusing on the inputs and the outputs, and then how to use them later.
Yeah, by and large. But then again, we have preferences. For example, for the inference, we use Kserve, right? So it might be that you don't like Kserve or you want something else, in which case maybe you would not use us for the inference, but you can still use the whole platform for the rest. It's just you will lose a lot, but it's still possible. There is no limitation in that regard. And the idea is not to add limitation in that regard. Thank you.
Thank you. So maybe one last question, and then you can ask the rest of the question in the break.
Thank you very much for the presentation. Really appreciated how you broke that down. I had a question related to the concept of versioning. I somewhat understand it from the perspective of you change the schema of your inputs or your feature extraction, and then you're going to break stuff. But what is the actual underlying intention with versioning, or how do you use it in your product? Is it that if you have breakages, then you can roll back to a previous version?
Exactly.
Or? Okay.
You can that's exactly the point. You should be able to roll back to the state that it was prior, and you should be able to update to a new state if it performs better. So if you do a bit of monitoring, you can always see, for example, if things start to decay, let's say, or like degrade in performances, in which case you might already have like another pipeline ready for taking over, but maybe in production it breaks for some reason. You should always be able to roll back. So the point of the versioning is to be able to roll back easily. So it's just a version, say version 2, bam,
yeah.
and that's all.